Alright, so oxidation reduction reactions are often really difficult to balance, and sometimes in oxidation reduction reactions, instead of being given the entire compound, you're given only the ions that actually participate in the reaction, like the one that we see above. So we're going to discuss a way to learn how to balance these reactions by using what's called the half reaction balancing method. There are two different types of these methods. There's one method in which the substance is, or the reaction takes place in an acidic medium, and there's another type in which the reaction takes place in a basic medium. So today we're just going to focus on the acidic medium. So we've got a reaction here. We've got the permanganate ion, which is being added to iron, and we see that we're getting iron out the backside, but a different type of iron. We get iron 3+, and then a new type of manganese ion as well, Mn2+. All right, and we should know that these different types of ions, Fe2+ and Fe3+, they have different properties. They may have different colors. They may act a little bit differently. So running a reaction like this may be purposeful in trying to obtain those different types of iron substances. All right, the first thing we're going to do is just assign oxidation numbers to everything. Over here, oxygen has a -2, and so if we do the correct algebra, we'll see that manganese is +7, and then the rest of them are actually fairly simple as we look all the way through. Iron's 2+ on the left side, 3+ on the right side, and manganese is 2+ on the right side as well. So let's write the half reactions for these two things. We've got MnO4, and as you'll notice, I'm actually going to take the oxygen with me. All right, that's negative. And that's going to fall into Mn2+. Okay, and I'm just going to leave it like that for right now. I'll come back to it in a second. Let me actually do a little erasing here. Okay, I'll come back to that in a second. All right, and then I'm going to write the other one right below it, the other half reaction, and that's iron 2+ on the left, and then that's going to go to iron's going to lose 1 electron and go to iron 3+ on the right. Okay, and again I said I'm going to come back to that in just a second. So we have to balance each half reaction. And as we look at the top one, that seems a little bit interesting because we have oxygen on the left but no oxygen on the right. Again, that's probably because the oxygen isn't really of care to us for this reaction. But in order to balance, we need it. We need it present. So if you have oxygen on one side and none on the other side, you can add water, so add water molecules, in order to add enough oxygen atoms to balance that particular side. Well, I have 4 oxygen molecules, or 4 oxygen atoms on the left. I need 4 on the right. So that means I'll need 4 water molecules, 4 H2O. All right? Now, as you may be saying, well, that's all great and good, but now I've actually added 4 H2O, so I've got 8 hydrogens on the right side, and, well, I've got none on the left. Well, we said at the beginning, at the onset of this, is that we're creating this reaction in an acidic solution. So that means there's a ton of hydrogen ions floating around. So in order for this reaction to take place, there must be some hydrogen ions that participate in the reaction. And so we can put them on the reactant side. So we have 8 hydrogens, 8H+. Okay? So now it actually looks like we've got a balanced reaction. 8 hydrogens on the left, 8 on the right, 4 oxygens, 1 manganese, 1 manganese. Okay, there is one last issue, however. We actually don't have a balanced charge. If you look on the left-hand side of the equation, we have 8+ things and 1 negative thing. That counts to 7+ overall. And on the right side, we only have 2+. So we actually have to add electrons in order to make the charges neutral, or the same on the left and the right, not neutral. So I'm going to have to add 5 electrons to the left side of my equation in order to make this actually a true statement, a true equation. So there you go, that green equation is now finished. We have the same number of charge left and right, and we have the same number of atoms left and right. Let's go take a look at the iron now. Down by the iron, we see that the balancing is really simple. We have 1 iron on the left, 1 on the right. It's just that the charges are different. So we're going to have to add one electron to the right side here in order to make the charges equal. Now I have 2 plus on the left and 3 plus and minus 1 on the right, so it's a 2 plus on the right as well. Okay, so now we have our half reactions essentially balanced. Now it's time to combine. Now when we do this, the first thing that we need to do is to make sure that the participating electrons are the same in the reduction as they are in the oxidation. And right now we see that the green equation has 5 electrons. The red equation only has 1. So we're going to multiply the entire red equation by 5. And if we do that, I think we are going to see that we get 5 iron 2 plus. We get 5 iron 3 plus, and we get 5 electrons. Okay? And so we're ready to combine our entire reaction and get a final answer for this particular equation. Alright, I'm going to do that. Let's see, what color do I want that in? Purple. Purple's nice. Alright, so we have 8 hydrogens, 8 H plus the permanganate, MnO4, the negative, plus 5 iron, Fe, 2 plus. Electrons cancel out, 5 on the left, 5 on the right, they go away. On the right side, we have Mn2 plus 5 irons, Fe3 plus 4 H2Os. And if you count the charges and you count all the atoms involved, that's a balanced equation. It's a big equation. It'd be very hard to balance that thing in the traditional method that we have learned. So that's why we learned this new method. All right.